Alright, so we're gonna get into rigid body, work, and energy. So every time we analyze the motion dynamics, of course we separate them into particles and rigid bodies. So we have already studied the work and energy for particles, and we will get into work and energy for rigid bodies. So review again. So your work, the amount of energy that is transferred by a force is going to act through a distance. Your kinetic energy is your energy due to a body's motion, and then because potential energy is your energy due to a body's position. Okay, this got to be a apostrophe. Actually, I think the editor or the author, one of them, got wrong here. Whatever it is, so just take it like this is for the motion, that's for the position. Yeah, so the highlighted points is going to be right here and right there. And your work again, your force and the distance. Yeah. We come back to our mathematical expression. So your work is, in this textbook they use U for symbol and F times D. Your work in energy unit, Newton meter, and we call that joules. So basically that's just force times your displacement, even though we call it D or distance in common word. Then forces may move by a different amounts because forces ain't the same. So they can be applied in different angle, different direction, and also different amounts. So it is represented by, for calculus-based dynamics, we use a U equal to integration F times, this is just a differentiation, little d, and then of course R, meaning like we want to move to backwards, mathematical operations. And here it is a diagram showing you your review for your work. Of course, so we have a different position here going from 1 to 2 and then 3 and then 4, and we calculate each step of them. So these are massless connections between the mass objects here. Kinetic energy of a particle, we go back to what we have studied for Ke, which is your kinetic energy 1 by 2 mv squared. Kinetic energy of a system of particles, we're going to put the particles 1, 2, 3, 4. Of course, you don't have a 4-particle system. We have a gazillion of the particles, right? It's a too simplified version of it, of course. And then we can calculate by summing them up using the same equation, 1 by 2 m. Of course, I represent the number of particles in that system, and then of course your T 1 by 2 mvg, the whole square, plus 1 by 2 ig, and then this one is omega squared. So we're getting into linear and rotational. You don't have to do this again. So I'm just gonna talk it out for you. So if you can at least understand that we're dealing with a system of particles, and every time we deal with a system of particles, we always have a center, which is represented by the big dot here at G. Anyways, in potential energy of a particle, single one, Bg, Mgh, Be, elastic, 1 by 2, coefficient of your spring. We had elastic example as a spring over there, so K. And then you can also say this is elastic constant is fine, and then x, the whole square for the displacement. And then your potential energy of the system of particles, we are going to look at the system in terms of particles in that system, and we can calculate by giving I for the total numbers of particles in that system, and we use the same equation here. And of course, for potential energy, you need a height, and that height is definitely calculated from the point G of that system. And then your elastic potential energy, we will use the same equation, 1 by 2 k and then a squared. Of course, here we're going to use a vector, which is your J, representing all particles. Energy balance equation, we will use kinetic energy initial, potential energy initial, and the non-conservative forces work. And then final kinetic energy, final potential energy, yeah, represented by the 2 here. Conservation of energy, your kinetic energy, initial, your potential energy initial, you sum it up is equal to the final kinetic energy and final potential energy, the sum of them. Yeah. So these are just a review from the previous chapters. Now we'll get into the rigid body. So when we take a look at it, your rigid body kinematic, this is just go back to the website and you can be able to see some animation, you know, in there. So here you're going to consider an unwinding spool fixed at its center being pulled by the rope like this, and that is wrapped around as an inner hub, which is this guy here. You know? So we can be able to see a little bit of interactive showing you the motion of that, you know, spool. See like how it's going in that direction. So now we've got the work done by the force, yeah, from here all the way to here is your distance. Because of this force, and we pull it, and it's going to come from this point all the way to the end. So the work done by the force F can be described as here is your work, and here's your force times your distance, which is that guy I just showed you, and as your force is going to move through at that distance of d. So can the work be described in a different way? So let's take a look at it. So force also creates a moment, yes, about the spool's center right there. So work may also be calculated using that moment. So we're going to use it. So your distance is d divided by r, yeah, this. And then of course your fr, and then this is going to give you the moment, okay, of that theta, okay. So we can identify the work in terms of force and distance, and we can convert that force distance to the moment about the theta, yeah? And that's just a center. Then we're going to come back here for the work equation. This is the same equation that we use for work. So here under special situations, work may be calculated using a moment. Here is what we have just calculated in the spool example. Your fixed point rotation is going to go point 1 to 2, and your work is done from point 1 to 2. And we are going to use, you know, moment instead of the force. So we're going to get like theta 1 to theta 2 representing how work's been done, and we're going to use a moment m differentiating against your theta angle. Yeah. The force-induced moment is going to look like this. So you have work done 1 to 2. Your theta 1 go to theta 2, and we will use the moment and differentiate it against that angle theta. Yeah. So right now you can't be able to see it, and I will show you, yeah, one by one later. And of course you only need to understand the definition. Will not really stress on the chapter 8 for calculation at all, especially calculus related calculation. So let's take a look at 8.2-2 to understand what's going on. So consider the following situation where a force of constant magnitude F is going to be applied to a pendulum right there over an angular distance theta, which is this guy right there. Yeah, we're going to rank the following situation in terms of the work done from greatest to the least. I'm going to make it bigger for you so you can be able to see it. So we are presented with 4 situations. So when you look at the A, you're going to see the force is going that way. You know, your force is 1 Newton, and your L is going to be 2 meters, and your angle is right there. And then you have your B, your force is still about 2 Newton, but then your length is now reduced to half. And this is going to compensate it, so A and B is about the same thing, yeah, about the same. Because you know, like you reduce half here, and then you increase half, you reduce half right, half here, and then you increase 1 here. Yeah. So this situation A and B is the same thing. You know, you will get the same, yeah, amount of work. And of course, if you put it into mathematical, you know, calculus-based equation, you're going to get the work done 1 or 2, going from position 1 to position 2. You're going to go from line theta to theta, which is this guy, and then your F, and then your length right here, your distance. Of course, when you do your trigonometry, you're going to get the cosine theta, yeah? differentiate against theta. So you would get 2 sine theta for this two situation right in here. Then you'll see you have 2 meter, the distance of L, and then 1 Newton force. And your D, you have a 2 meter, okay, and moment is given to you, that is a 2 Newton meter, okay, moment. So the only difference between C and D is that this is work is defined in terms of force, this is work is defined in terms of moment. Moment is force and the displacement, which is your meter here. So here you can calculate work done by using the force, and then your distance, which is your displacement, going from here to here, the angle. So we have F and then L and then theta, and you're gonna get like a 2 theta, for that, because we put 2L here and then F is 1, so when you calculate it, you're gonna get 2 theta. We try to write it only theta, and we don't bother about writing in sine, and that's because we're just assuming that we're dealing with the very small angle because of this moment. Moment means it happens in a very, very small unit of time, so therefore that's why we call it a moment, a moment of the time. So therefore this angle got to be very, very small, and that's why we're neglecting the sine or cosine trigonometry aspect of it. We just go straight on theta. So here, going 1 or 2, in terms of moment, we can calculate moment times the angle directly, and your moment is 2, so therefore you get 2 theta, so the C and D is the same thing. So you've got 2 theta, and then you have 2 times the sine theta, okay? So if you take the sine of the theta, you will definitely get smaller than 2 times the theta, okay? Because sine theta is less than theta, okay? So that's just showing you when angle increases, sine theta is less than theta. And this is not by Zeiss, this is by calculation, values. So sine theta value is less than 0. This one we go by moment is just a speck of time. So sine theta is relatively about the same as theta in small, very, very small angles. Therefore we can use it directly. So your answer is CD and then on AB. Then of course we will go into kinetic energy. For rigid body, so we use the same equation, 1/2 mv squared from the last chapter. And your particle is going to go translation, and then your rigid body will translate and rotate in general planar motion. And how will this affect your kinetic energy equation? So let's take a look at it with this interactive on your website. So this guy right here, so which bar has a higher kinetic energy during the motion? So let's take a look at it. So you're seeing the translation with the rotation, So you can see that it goes up, it ends up at the same, And then we're going to come back and continue to learn about this rigid body that go translation and rotation at the same time. So a body may possess kinetic energy due to its rotational motion. So using the kinetic energy for a particle as a reference. So guess how the rigid body kinetic energy due to rotation is calculated. So let's take a look at it. We're going to use the same T, which is a kinetic energy 1/2 mv squared. So that's the kinetic energy all for a particle. Alright, so when we come into the rotation, we are going to use a different symbol to identify that. So we use T 1/2 and then I, right? That's just O, which is showing you a point in the system, and then omega, the whole square. This is your angular velocity, which is this is regular, which is linear. I call this regular, meaning it's just linear. Velocity that's angular going in rotation. Your mass, of course, this is moment, mass moment of inertia. Then we will go to this 8.3-3 interactive. So what is the kinetic energy of the following object? So see it, let's go that way and then go that way. It looks like translation to me. So we define, oh, it's just a pure translation, we can calculate kinetic energy 1 by 2 m and v squared. So what is the kinetic energy of the following object is going in a rotation? Yeah, see, and every time we do the rotation, we identify the O, which is your axis of rotation, and we can be able to calculate it by using kinetic energy for pure rotation 1 by 2, and then mass moment of inertia at O, and then your angular velocity, the whole square. What is the kinetic energy of the following object? So first is go that way and then come back down. Yeah, so it's general planar motion. So therefore we're going to calculate it by adding it up. You know, first your translation and the second is your rotation part. So 1 by 2 m and then vg the whole square, 1 by 2 mass moment of inertia, and then angular velocity the whole square. So now we go back to our lab, and this is what I say: if you want to calculate, even if it isn't included in your curriculum, you can be able to use this, but you have to go with segment over segment. Yeah, depends on how it rolls in that track system you built. All right. Okay, so we're done with this interactive activity. So we come back to here for kinetic energy for pure translation. We would write this way: so kinetic energy equal to 1 by 2 mv squared. Pure rotation, kinetic energy equal to 1 by 2 mass moment of inertia, and then you're gonna have like a angular velocity the whole square. And don't forget, review your mass moment of inertia, because this moment of inertia is nothing but just a resistance. Like I say, something that is staying want to stay. It doesn't want to move. So when it is subjected into a motion, it's going to resist that motion. So how much resistance that object or this rigid body offers to your angular acceleration about that point O here, trying to resist the potential to move. Alright, then general planar motion, where your translation and rotations are happening together. So we will add them up, of course. It's a common sense. So if you have kinetic energy, your translation, and then your rotation, we add it up just like that. So 1 by 2 mvg squared plus 1 by 2 ig, and then omega the whole square, and g is your point in the system. I'm going to go back. Okay, when I say a point in the system, it's your datum, which is your reference point. It's a mass center of all the particles in that system. Alright, so consider the following situations where the same bar is translating and or rotating with the given linear and angular speeds. So rank the amount of kinetic energy each bar has from greatest to least. So let's take a look at it in a bigger picture. I'm just going to go ahead and put the equations for you so you can be able to see it. So the very first thing that we look at it is you have your velocity, yes, and then of course your length, and then omega is your angular velocity divided by 2. And you do have your kinetic energy, how we calculate for translation, is going to be like this. Okay, so mvg, and then 1 by 8. Why? It's because it said it so. V is this amount, so we put it into there. So you're gonna get 1 by 8 ml, and then omega the whole square. The second one, we do the same thing. Second one is you have a rotation and translation with this arrow, 2 of them, so 2 motions going on. So therefore, we have to add them up. So you have your translation site, and you have your translation site, and then you have your rotation site. Translation site, you are going to put this, which is L omega divided by 2 into velocity, and calculate the same thing. And here you have your I, and then you are going to calculate omega, just leave it there as it is, and we are going to translate I into ml the whole square, because you will have to get I from this velocity. So you're gonna have the issue understanding, how we write I. The moment of inertia is where's my pen? Let me see my pen. Okay, so how we go from there to there is because of this structure, and this is a rod. So every time you you deal with the rod, we go Ig is it has a specific coefficient, which is 112. Yeah, 1 by 12. So 1 by 12, and then m, and then the length of that rod, which is the whole square. Okay, so that's what we use in there. Yes, so you get 1 by 12 m, and then L the whole square. So that's what I put it in there because it is a rod. Okay, ROD. So every time we deal with a rod for mass moment, we use this, and we're gonna put the mass of the rod in there, and the length of the rod, which is L. Okay, so that's, I think, one new thing that you will learn, and that's how we get it. Yes, and V, of course, you go and put it in there for you. Don't ask me how do we get it. There's another mathematical course that you have to take in order for us to calculate different shapes. Yeah, this is just a simple rod, different shapes for different mass moment of inertia. So, that's the reason why me, like headbutting with the administration to try to make them understand, because they cannot be able to understand. Well, I don't think they ever took the dynamics. I don't know. So anyway, so it has a lot of math components, in it. You can build a building or a ship or a train or a plane in a very easy way. No, it's very complex. Yeah. So anyway, C, we will do the same thing because it has a rotation. So therefore we use a rotation formula, and this one has another rotation. It is the rotating, yes, orientation of that rod is different. So therefore we use the same thing, and we calculate it and we plug it in. Okay, the V, of course, into it, and you will get that. Yes. So therefore now we will compare the result. So after comparing, we got B and C. Okay, they have the greatest, because if you look at it, okay, when you calculate, you're gonna end up about the same. And then A is going to be less because that's 1/6 and that's 1/8. Okay, and then D is going to be least because it's 1/24. Yeah, so we just, every time you have a fraction smaller, then your value is going to be smaller. So therefore we rank it this and this is the greatest, followed by this and that. Okay, because if you don't believe me, you can solve it. Yeah, if you solve it, you'll get this. If you don't know how to solve it by hand, you can use your AI, and it will going to show you the same thing. Yeah. So BC followed by A and followed by D for this example. Then we will go into potential energy for rigid bodies. Energy stored due to a body's position. Yeah, here are different heights in there. So here is your loop. Yeah. Then we'll go to this interactive. So discuss the change in potential energy of the pendulum after it moved. And it moves that way, and then ended up like that. Okay. And then, of course, your potential energy of a rigid body depends on the position of the center of gravity, which is this guy right there. It goes and tosses and then drop and position this way and ended up like that. So therefore, change in potential energy is going to be 0 because this height is the same. Even though it oriented this way and oriented that way, the way that it is staying, okay, is different as an object. But as a G point, and they have the same height. Okay, so therefore it has the same potential energy. Then we come back here and we will review gravitational potential energy. So the height is very important in potential energy in terms of gravitational force. Is measured with respect to, again, the center of gravity. Okay, so we use a VMGH, our famous equation. And elastic for the spring and stuff like that, then you do potential energy is half, and then spring constant, and then your displacement, the whole square. Let's take a look at the work energy balance. So here is our balance work energy equation. So you have kinetic energy initial, potential initial, and non-conservative work. And then you have final kinetic energy, and then you've got final potential energy, and they balance. Balance means they equal. Yes. conservation of energy is not the same as energy balance equation, different, because it doesn't have that. So we have initial situation, kinetic energy plus potential, and final situation, kinetic energy plus potential energy for the work conservation of energy. Then system of rigid bodies. Now we think about the system. We start with the particle. We study that a lot of particles in a rigid body. So there's a lot of particles in a rigid bodies. Then we've got these rigid bodies in a systems. Okay, many different ways you can study. Little things, medium things, and medium things, have bigger things. Yes. So anyway, so the whole multiverses or universe or the space we're in, the nature of that thing is like that. So anyway, and we are somewhere around here. A system of bodies, system of your organs. So we have lung, and we have heart and brain and sight, nervous system, muscle, right? So each one of them is a component of the system, and in each one of them also you have a lot of cells of atoms. Oh my gosh, so many levels of layers in there. So anyway, so individual forces may move through different distances. Okay, so work is calculated the same way. Individual forces, they're going to move through different distances when we consider the system of rigid bodies. Then of course we always have to think about the non-conservative forces where you lose them. They cannot be stored back or recovered. So internal non-conservative forces, joints, bearings, material, hysteresis. So these are many different components of the system of rigid bodies. Rigid bodies, of course, when we think about the mechanical thing, we do not care about human system at all because that is bio, but it works the same thing. Rigid body are just lifeless bodies, many different objects and particles that we build in mechanical, even though we try to give you the example in human way as well, because dynamics is also used in a human system, bio chemical system, and this is a pretty mechanical system with non-living atoms and elements. Okay, so kinetic energy, we're going to write it T, and that's the sum of the kinetic energy of that system. I mean, is going to refer to many different rigid bodies. And then potential energy, of course, sum of your potential energy, that many. This I can be particle, this I can be rigid bodies. Okay, depends on how complicated your system is. So calculating energy using the system as a whole may be difficult. It's very easy to explain. It may be difficult unless the system is rigid. Okay, so energy incredibly difficult in our system, very difficult to calculate. We can come like as close as possible. Of course, even with the rigid body system still is very complicated. Because rigid body still is composed of particles anyway if you go down to different levels. Now come back to a solid cylinder and a hollow tube rolled down and inclined. So both cylinder and tube have the same weight, radius, and then start at the same initial height. Then you have to think about which will reach the bottom of the incline first. So I have already shown you a video with the mechanical lab video for the incline and slope where we roll down a hoof and then a sphere and a disc. So anyway, here we have a solid cylinder, a hollow tube, and they're gonna roll down this inclined structure right here. And then we have to decide which one is going to reach the bottom of the incline first. So when you compare cylinder and tube, okay, cylinder is going to go to the bottom first. That's because it's faster. So why is if you think in a common sense, it has a less rotational energy, okay? Because this one will go with more rotational energy. So it has less rotational energy, yes, compared to that, its counterpart, and more translational energy. So therefore, it's going to go faster. This one is roll. It won't translate as much as this guy did. Okay, that's why this is gonna get to the bottom, okay, fast. Your tube is gonna lag so behind. And in a way, you might think like tube is gonna go down first, but it isn't. Okay, this guy is gonna go down first. It's because when you take a look at the for cylinder calculation. So if you want to think about it, when you calculate it with like the conservation of energy, we have, of course, we don't have this because you start with 0 velocity, so you have a height, and then this potential energy you will use it for kinetic, some portion kinetic energy for motion, and the other one is for potential energy, okay, to get to this point. So you're going to get 1 by 2 mvg, and then you're going to get mvg squared and 1 by 2 mass moment, and then times the angular velocity. Yeah. And of course, we can be able to calculate the linear velocity against angular velocity by multiplying with this radius, okay, of that sphere, cylinder, sorry, and also this disc tube, which is the tube. And we can be able to calculate square of that, yeah, by using this equation. Yeah, so we're getting this guy out of it, yes, and move everything else on that side, and we can be able to get this. So 2mgh 1 plus ig divided by r squared. So don't forget, we are also replacing, okay, this little guy here with that too, and that's how we're getting this r into in place of this angular velocity. Again, you don't have to calculate it. I'm just saying use this and this in order for us to deduce vg squared. Yes, and that's your velocity. You need this in order for us to understand which one is faster, which object is faster. Yeah. And then of course we use the constant acceleration equation. I know one of the students want to use this equation a lot. I think he got it from physics. So anyway, so of course we can be able to calculate that constant acceleration, and we will put this into there. So therefore we get mg(h)r squared divided by delta s and then r squared plus ig. So this is where you can be able to get the acceleration. Yes, so that's the rate of change of velocity. So what you're learning here is for cylinder and a tube here, they're gonna roll without slipping. So they're gonna convert that gravitational energy that caused that motion into the potential energy. Convert that gravitational potential energy to motion, which is this guy. Kinetic, translational kinetic energy. And the other one is it also has a rotational kinetic energy, translational and the rotational kinetic energy as it roll and also go down. Yeah, roll means rotation, going down is your translation. So you have a general planar on both situations. When you calculate the translation kinetic energy, we go by, remember, 1 by 2 mvg squared. And the rotational, we go with the 1 by 2, which is this guy, ig omega squared. Yeah. And if you use the conservation energy, I already showed you how to calculate this from here. Yeah. And then we also come up with the linear and angular relationship like that. Yeah. And you rewrite everything. Okay. And you ended up like this. Okay. So this is what we've got. So the smaller the term, this guy right here is very important. If you can see it, I'm gonna just circle this for you. So the smaller that term, the greater that is going to be, because they're inversely proportional to each other. Yeah. So for a cylinder, I'm just going to take that out for you. Your IG, for a cylinder. So that's easier for you to see it instead of the entire entire equation. So Ig is equal to 1 by 2, okay, mr squared. So this is your review from chapters before us, yeah, mr squared. So if you don't remember this, I'm going to write that down for you. It's 1 by 2 mr squared for getting Ig. And then, of course, for if you calculate it, if you calculate it, move this r to the side, you're gonna get like this. I'm just gonna write that down for you here. So you get 1 by 2 m, all right, which is this guy, mass. For hollow tube, okay, for hollow tube is a different thing. So your mass moment of inertia for hollow tube, okay, Ig is just mr squared, okay, mr squared. Don't ask me why this is only mr squared and there is no half. That's because of the shape. Yeah, I already told you. Rod is 1 by 12. This guy is 1 by 2, and this guy is just 1. Yeah. So when you calculate that, we do the same thing. Move this r to the other side. Yeah. So if you move the r to other side, you're gonna get like that is equal to m. See, now you can see it. See, so this is a mass, is 1. This is a mass, half. So for it to roll, okay, you're carrying only half of the mass, so it will go down fast. Yeah, this one is a 1 mass. So that's how we calculate. Yeah, so the cylinder has a smaller Ig over r squared. So that's a rotational. This thing is telling you that it needs only less rotational energy and with more translational energy, so it will go faster. Yeah, this one need more rotational energy. Yes, so therefore translation is the same anyway, because this is the same Zeiss inclined that they're rolling. So for rotational, you're spending only half m. For rotational, you're spending m here. Yeah. So therefore, this will go down faster. The next question is, what has the potential of making the cylinder slower than the tube? Okay, so now you want to make the cylinder slower than the tube. You want tube to go down first. So what can you do? So the first thing is, okay, so this is asking you what has the potential. It's a very, very tricky question here that you're reading. So what has the potential of making the cylinder slower than the tube? So it's just asking you the potential. It doesn't ask you the correctness of the statement, okay? So what is true is actually E, S in statement, yeah? So the tube will always be slower than the cylinder no matter what the relative values of m and r are. But the question doesn't ask you, show me the correct statement. It's asking you what has the potential of making the cylinder slower than the tube. So if you can't be able to make, the mass of the tube, less than the cylinder, or if you can be able to make the r of the tube, okay, which is the radius, of the tube greater than the cylinder, then you have potential to make the cylinder slower than the tube. That's what it said, yeah. If you so just be careful in the way this question is asking. It wasn't asking you to choose the correct statements. It's asking you the potential to make the cylinder slower. If you can reverse this, or if you can reverse that, then there is a potential that this cylinder could go slower than the tube. So it's a tricky question for you here. So anyway, this is just showing you the acceleration and the Ig of the cylinder and the Ig of the tube that we have already calculated from the previous slides in there. Again, you don't have to do a calculation. Then we go back into the example problem, which is not included in your curriculum, so therefore you don't have to do that. Just if you could listen to this, it is enough. Like chapter 7 and 8 is tied for particle and rigid body. So that's why I'm putting the lecture at the same time for you for chapter 7 and 8. Okay, yeah, okay, that's it for this chapter.